Hey there, organic chemistry students. Mr. Brown here, and this is your lecture for Wednesday, October 2nd. We left off on Monday wrapping up how to name the simple alkanes, and we are going to look at some of their properties and representations throughout the rest of this chapter. Here on this slide, we see a chart giving us the number of constitutional isomers of different alkanes. Alkanes containing 3 carbons through 40 carbons. The purpose of this slide is just to demonstrate once you get up past 10 carbons or so, the numbers of isomers of the long chain hydrocarbons increase exponentially. It's also a good place to say, essentially, now that you understand how we're going to name organic compounds, you might not know the entire set of rules for nomenclature yet. It's a good place to stop and say, hey, one way that you can check to see if a molecule is an isomer or is it completely different from another molecule is to name the two molecules. If they come up with the same name, then they are constitutional, or they are the same molecule. If they come up with different names, but they have the same counts of atoms, then then they would be considered stereoisomers of one another. So we see that premise in action on this slide. If we count really, really closely, we would find that both of these molecules contain 9 carbons and 22 hydrogens. And so we can say from that information that one of two things is possible. Either these molecules are constitutional isomers of one another, or they are the same molecule. So one way you can tell, perhaps the easiest way to tell, is to name the molecule. If they are the same, then it is the same. If they have different names, then they are just constitutional isomers of one another. The first molecule here, if we look for the longest chain that has the most substituents, that should be the longest chain with the most substituents. This is a 1, 2, 3, 4, 5 carbon chain. So this is going to have pentane as its base name. We see a methyl group on carbon 2, a methyl group on carbon 4, and an ethyl group on carbon 3. So the name of this molecule would therefore be 3-ethyl 2,4-dimethyl pentane. Our second molecule here, if we find the longest parent chain with the most substituents, it appears to be this chain here. That chain is also 5 carbons long, and we have methyl groups on 2 and 4 and an ethyl group on 3. So the name of that molecule should therefore be 3-ethyl 2,4-dimethyl pentane, proving that these are not just constitutional isomers of one another. These are in fact the exact same molecule, just drawn in a different orientation. You'll notice that the next part of the text describes the sources and uses of our common alkanes. I am going to hold that discussion, since this is a video, for lab next week, in which we are going to have a whole discussion about the fuel usage for our simple alkanes, how distilleries work to fractionate the different compounds that we find in these hydrocarbons that we dig out of the ground. We're going to do a distillation on our own and kind of discuss all of these topics together in lab. So you should not have any homework questions that relate to any of this material. This section just asks you to identify constitutional isomers. It's really interesting stuff to me, so if you want to kind of go ahead and read ahead, again, we'll talk about that next week when we do a distillation of some simple alkanes. The next topic we come to in the text is that of Newman projections, and this is a topic that we covered or started to cover last Thursday in lab, so I feel pretty certain that you have somewhat of a grasp on what a Newman projection is trying to tell us, but we'll quickly review. Conformations are different arrangements of molecules that have carbon-carbon single bonds, because molecules where they have carbon-carbon single bonds, they are free to spin at those locations. This leads to different shapes called conformations. Some conformations are higher in energy level than others. You can begin to think about conformations that are more crowded than other conformations that are less crowded are going to be less energetically favorable. It's going to require some energy to move into more crowded conformations. And so Newman projections allow us to evaluate whether there is a bunch of crowding in a certain conformation or there is not a bunch of crowding in a certain conformation. We see the common projections of ethane here. This is used to kind of get our bearings about what each of the different projections is trying to display to us. And in the Newman projection, we see that the front carbon is symbolized by the center of the dot there, and the back carbon is the circle in the Newman projection, and the bond between the two is in between, kind of behind the dot. And then each of the substituents is drawn bonded to either the back carbon on the circle or the front carbon at that point. The conformation of more complicated molecules can also be drawn as well. Here we see a dibromobutane species, and if we look down the carbon 2 carbon 3 bonds, we might see a Newman projection that looks like the one given here, where the front carbon has a bromine, a methyl group, and a hydrogen bonded to it, and the back carbon has a bromine, a methyl group, and a hydrogen bonded to it. There is no spatial information in this molecule here. We're not given a line or a dash line or a wedge to let us know whether the bromines are in front or the carbon or the methyl groups are in back. So just given that molecule, we could kind of draw whatever Fisher projection we wanted, or Newman projection we wanted rather, and call it correct. Here we have a little bit more complicated Newman projection problem. We're given a complex alkane here, and we've been asked to cite down this particular bond and draw a Newman projection. And if we did that, the Newman projection would look like this. So we can see with the observer looking down this bond here, we should have a front carbon and a back carbon. The front carbon only has a methyl group shown bonded to it, meaning there has to be some hydrogens here as well. And we can see that on the Newman projections, where the two hydrogens are bonded to the front spot, and the methyl group is also bonded to the front spot. And then on the back circle, on this back carbon here, we have a tert-butyl group here, another tert-butyl group here, and there is a hydrogen hiding here to fill out the valency of that carbon. And the two images that we've seen down here, we see the tert-butyl groups on the back carbon here and here, and then we see the hydrogen that's also hiding out on that carbon as well. They show the equivalency. Chemists in their fashion love to abbreviate, love to make things easier to write. You'll often see the abbreviation T-BU to stand for the tert-butyl group. Sometimes you'll even see ME for methyl instead of the CH3. Next, we'll start to analyze the difference in energy between conformations of different molecules. And we can see here a definition of what is known as the dihedral angle. And we need this definition to kick off this discussion. The dihedral angle is the angle between two atoms on either side of a carbon-carbon bond. And you get a graphic here that shows you the depiction of what a dihedral angle is. That probably helps you visualize it better than the wording there. So dihedral angles are shown here on the slide. With infinite degrees of freedom to rotate around that bond, you can have infinite number of conformations of that molecule. But we tend to focus on two of the most important conformations. The staggered conformation is given here on the left, where all of the atoms on the opposing bonds are as far apart as possible. Their dihedral angles are as great as possible for all 6 of the atoms represented there. That is what is known as the staggered conformation. It is always the lowest in energy versus the eclipse conformation that you see on the right. The eclipse conformation has all of the atoms in line. They're drawn right next to each other so that we can see all of them, but we're in the eclipse conformation, we're understanding that those atoms are all basically at 0 degrees to one another. They're in perfectly straight lines. And those are the two most important conformations, because the staggered conformation is always the lowest energy conformation of any molecule, and one of the eclipse conformations is always the highest energy conformation in any molecule. There is still some debate as to where the extra energy requirements for the eclipse conformation of ethane versus the staggered conformation of ethane comes from. It might be theorized that the eclipse conformation has the hydrogen orbitals bumping into each other, and that's why it's a higher energy requirement. But hydrogen is not quite big enough for that to be the case. They're so far away in these molecules that their electron orbitals would not really overlap. The most current accepted explanation says that the molecular orbitals formed in the molecular orbital theory show favorable overlap when in the staggered conformation that disappears in the eclipse conformation. And this is the source of the extra energy needed to force ethane into an eclipse conformation. So we actually have numerical values for the amount of energy that's required to rotate a hydrogen past another hydrogen or through the eclipse conformation for the ethane molecule. And we can see here on this slide that that energy cost is 12 kilojoules per mole. So to turn 1 mole of ethane molecules from the staggered conformation through the eclipse conformation requires 12 kilojoules of energy input. So on this slide, we can see that we are going to draw a Newman projection looking down the bond between C2 and carbon 3 in a molecule of propane. And propane has 3 carbons, so the bond line structure for propane looks like this. And of course, there would be some hydrogens here. Here and here. And since this question is asking us to look down the bond between C2 and C3, if we number our carbons 1, 2, and 3, that means we would be trying to draw a Newman projection looking down the bond indicated by the arrow there. And we see that on the front carbon, there will be a methyl group and 2 hydrogens, and on the back carbon, there will be 3 hydrogens. So the staggered Fisher or staggered Newman projection will look like this, with a CH3 in one of those spots, an H and an H and an H and a hydrogen there. So that would be the correct staggered Newman projection looking down the bond between C2 and C3 in a molecule of propane. And the eclipse projection would look like this. And of course, this would be the higher energy conformation, and so you would draw the eclipse conformation in these spots to complete the diagram. And the staggered conformations in these spots to complete the diagram. We saw on the previous slide how it requires 12 kilojoules per mole of ethane to spin that mole of methane molecules from the staggered conformation through the eclipse conformation. And because it requires 12 kilojoules per mole, and there will be 3 sets of hydrogens interacting with each other when that rotation takes place, it is therefore assumed that one hydrogen moving past another hydrogen from the staggered to the eclipse through to the next staggered conformation requires 4 kilojoules per mole per hydrogen for that total of 12 kilojoules per mole. And we see here, if we evaluate the conformational analysis of propane quantitatively, it requires 14 kilojoules per mole of propane molecules to rotate to force that C2C3 rotation, whereas it only takes 12 kilojoules per mole, if you remember, for ethane. So what that means is there is an extra 2 kilojoules per mole necessary to move that molecule from the eclipse, or from the staggered rather, through the eclipsed conformation. And because of that, that means we can assume that the extra 2 kilojoules of energy comes from the necessary overlap of the methyl group moving past one of the hydrogens. And since there's an extra 2 kilojoules of energy there, it is assumed therefore that the methyl group moving past a hydrogen in order to move from the staggered through the eclipse conformation has an energy cost of 6 kilojoules per mole. So here on this slide, we are asked to apply that knowledge that a methyl hydrogen overlap requires 6 kilojoules per mole to overcome the barrier of rotation, and a hydrogen-hydrogen overlap requires 4 kilojoules per mole to overcome the energy barrier of rotation. We are asked to consider the following 2 molecules, 2,2-dimethylpropane and 2-methylpropane, and we are asked to determine what the energy barrier to rotation is for looking down any of one of the C bonds. So this question is essentially asking you to draw one of the molecules, or both of the molecules in this case. We'll draw one of them though. We'll do 2,2-dimethylpropane. So if we draw a propane molecule, to get 2,2-dimethylpropane, we'll put 2 methyl groups on the second carbon there. And it says we can look down any one of the carbon-carbon bonds. And so we're going to look down the carbon-carbon bond here and draw a Newman projection for the view that we would see there. So there would be 3 hydrogens here on this carbon that we have not drawn. And so if we treat the first carbon there as the dot, all we have to do is bond 3 hydrogens to that carbon. Then we can show our back carbon, and we see our back carbon has 3 methyl groups bonded to it. And so, to perform one rotation of this molecule from a staggered conformation that we've drawn here to the next staggered conformation, a 120-degree rotation, we see that we would have 1, 2, 3 methyl hydrogen overlaps in that action. We know that each one of those overlaps has an energy requirement of 6 kilojoules per mole. So this has an energy barrier rotation to 18 kilojoules per mole. Now we are presented with a new question. Draw the lowest energy conformation of butane looking down the C2C3 bond. Butane is the 4-carbon simple alkane. So that is what a butane molecule looks like in bond line structure. And if we draw a Newman projection looking down this bond here, fill in the hydrogens of interest, may help us draw that Newman projection. We know we were trying to draw the lowest energy conformation of this butane, so I know I'm going to be drawing a staggered conformation of some sort. So I will start with the front atom here. Put a methyl group on one of its bonds, 2 hydrogens on the other bonds. And then on the back atom, when it's time to fill in the back atom and determine what the lowest energy conformation is for butane, I find that I might have a choice now of where I need to put that methyl group to give me the lowest energy conformation. The methyl group can either go here, here, or here. These two positions put the methyl group really close to this methyl group. This position, called the anti-position, puts it as far away as possible. That is the correct position for the lowest energy conformation of butane. So the methyl group should go there, and the two hydrogens should be here. So quantitatively, for the conformational analysis of butane, we can see that the highest energy barrier to rotation occurs when the two methyl groups must eclipse each other, and the two methyl groups eclipsing each other along with the two other hydrogens eclipsing each other has an energy barrier rotation of 19 kilojoules per mole. Even the other eclipse actions of the butane molecule require a substantial amount of energy, because in those cases we have a hydrogen and a methyl eclipsing each other twice, along with the other two hydrogens eclipsing each other, and we can see that that has an energy barrier rotation of 16 kilojoules per mole. Also, on the conformational analysis of butane, we see the lowest energy conformation here, and we also see that when the methyl groups are beside each other, the graph doesn't go down as far. There's actually 3.8 kilojoules per mole energy difference between the conformation that has the methyl groups beside each other and the conformation that has the methyl groups as far away from each other as possible. Chemists have some standard terminology in order to describe these different non-degenerate anti and Gauss. Chemists have devised some standardized terminology to describe these different staggered conformations that we see in these molecules. We use a system called anti and Gauss conformations in order to make these descriptions. Anti-conformations are the conformations that have the larger groups, the groups other than hydrogen, as far apart as possible. And Gauss conformations are those conformations in which larger groups, such as methyl groups, are staggered but yet beside each other. Those larger groups that are staggered but yet beside each other undergo what are known as Gauss interactions. And Gauss interactions are where the methyl groups are now large enough that their electron clouds do interact with the opposing methyl group. And these are called steric interactions, which is related to atomic arrangement. Steric interaction and torsional strain are different. Torsional strain is the very first interaction we talked about for the Newman projections, and that had to do with molecular orbitals having favorable overlaps, whereas the steric interactions are the electron clouds of these large methyl groups actually bumping into one another. From that data, we can then deduce that the eclipse of the two methyl groups has a total energy barrier rotation of 11 kilojoules per mole. Again, here we're asked to put our new knowledge to the test, considering the following compound, and they've given us a bond line structure of 3-methylhexane, and ask us, rotating only the C3C4 bond, identify the lowest energy conformation. So to do that, we're going to need to draw a Newman projection looking along the C3C4 bond and determine where we need to put those substituents in order to give us the lowest energy conformation. So I will redraw in here my 3-methylhexane. And the methyl group is actually shown with a wedge indicating it is coming out of the page at us. There will be a hydrogen going into the page in that case. And there will be 2 hydrogens on the number 4 carbon as well. So it says rotating only the C3C4 bond. So if we look down the C3C4 bond, and in this molecule, because of the methyl group, that is necessarily carbon 3, making this carbon 4. And if we draw the Newman projection from that viewpoint, we would put carbon 3 as the front carbon. And carbon 3 has, we know we're going to draw a staggered projection. And carbon 3 has an ethyl group, CH2, CH3. So that is this structure here. That's an ethyl group, CH2, CH3. A methyl group, and I can just put the methyl group here. This is our methyl group, the wedge. And on the other side is a hydrogen. So our carbon 3 has an ethyl group, a methyl group, and a hydrogen. That's our front carbon. Now if we draw our back carbon with our circle, and we know we're going to draw a staggered conformation. Those are always the lowest energy conformations. We're going to decide what would be the lowest energy conformation to draw for this molecule. We need to decide what we have to draw on those lines. So a bonded to carbon 4 is an ethyl group, along with 2 hydrogens. As we discovered in the previous discussions, what we want to do is get the large groups in an anti-position. Since the large groups here are the ethyl groups, it would make most sense to put the ethyl group on the back carbon as far away from the ethyl group on the front carbon as possible, placing the hydrogens beside the large ethyl group on the front carbon. Here we have drawn the lowest energy conformation of 3-methylhexane looking down the C3C4 bond. Given this information, I hope you can now draw the highest energy conformation for this molecule looking down the same bond on your own.